Okay, so let us start the second part of the lecture, which will be arc length and parameterization. But before that, if you don't mind, let me solve this exam question for you. So the exam question is the curve y equals to sine x with x between 0 and pi over 2 is rotated about the y-axis and forms a ways, a v. Determine the volume v. Okay? So here, if you don't mind, let us try to solve, or at least contemplate a little bit about different methods here. Of course here, because that is rotation, I will put slicing aside. So either solid of revolution will be a good idea, or cylindrical, the method of cylindrical shell. But let us get an overview what is going on. So the function involved is the sine function between only 0 and pi over 2. So it's a very famous function. So this is a function like that, for example, and this is pi over 2. And this is my 0, so this is function y equals to sine x. Okay, but which part is being rotated? The sine x between 0 and pi over 2. So be careful. X is between 0 and pi over 2, and then is rotated about... Okay, so it means that this region is rotated. Do you agree? This is the region I have. And I want to rotate this about the y-axis, and it is going to generate a waves, and then you want to calculate the volume of that object. Okay. There are different ways, by the way. You should be a little bit creative. For example, I hope that you can see that this method of cylindrical shell is very useful for this one. If I want to rotate this one, by the way, this will not generate a waves, does it? So probably they mean this one generates a waves, because that would be outside the waves, yes?
Don't you have to take the...
Pardon?
Sorry. Yeah, don't you have to take the inverse, the arc sine?
No, just I want to understand what the waves is first, because the curve is this one. I hope that you see that if it is between 0 and pi over 2, if I rotate this one around the y-axis, a little bit of imagination will help me to see that this will not generate a waves. Does it?
Well, inside of it, it's a very...
Yes, but inside of it. So it means that the volume, the region that should be rotated is this one, not this one that I hatched in blue.
Yeah.
Yes? Okay, so that's important. Okay? So, well, let me, for example, this one. This is the volume. This is the region I want to concentrate on. This region rotated about the y-axis will give me the waves that I want. Yes?
So when you ask for the volume of the waves, then you're interested in how much liquid we can...
Yes, we can put it in the waves. That's the meaning of the volume. Yes? So that's why I have to concentrate on the green part, not the blue part. But of course, if you calculate the volume of revolution for the blue part, you can see that this one will generate a cylinder. You already know the formula of the cylinder. You can subtract and you see what happens inside. Okay? But let us concentrate on the green one. So if I want to find the green one, I want to slice it in this way. I want to use a cylindrical shell, so that I just described for you. But be careful, your shell will be something like this. Your thin rectangle that you need is this. And you can imagine when I rotate it, it will generate a shell. The point is that the next shell is not of the same height. The height of the shell will also change. Is that clear? Okay. So now tell me, this is why they have done it in a way that just knowing the formula might not be enough. Or, if you want, you can do this one and subtract it from the full cylinder. That's up to you. Which one you prefer? Do you want to start from scratch, or you want to use the formula that we had? Because you know that this picture we had was this one. This one we had. This one was the x-axis, and this one was a function. Here, and this was the rectangle as an element that I told you. One part of this is on the x-axis. But here, my element, one face of it is on this line, which is 1. And one part of it is on this curve. So it's not exactly this problem. Yes? Either you can start from scratch, or what you can do, you can concentrate on the one below. But I want you to understand, if you rotate the one below, that is not the volume of the ways. You have to also find the volume of the full cylinder and subtract them. But the benefit of the second one is that you don't need to start anything from scratch. Okay? So let me use the one below first in the blue region. And can you tell me what will be the volume if I rotate the blue region about the y-axis? That's exactly my formula. So volume of the blue region is equal to 2 pi integral. The lowest x value is 0, the highest one is pi over 2. But my formula, unfortunately, I erased that. The formula was what? 2 pi integral from a to b, x f of x dx. So x is just x, but f of x in this case is sine x, and then dx. So this is the volume of the blue part. Yes? But then the total volume, the volume of the whole region is a cylinder. Yes? The total volume, you don't need even an integral for it. What is the total volume? If you rotate this about the y-axis, hopefully you agree with me, you generate a cylinder. The height of the cylinder is 1. But what will be the area of the base of the cylinder? Is pi, yes, multiplied by what?
Pi over 2 squared.
Pi over 2 squared, very good. Because this will play the role of the radius, this length. Pi is just pi, radius squared, multiplied by the height, which will be pi cubed divided by 4. Is that right? So then it means that the volume of the vase is equal to the total volume minus volume of the blue. Yes? This is one way of doing it. But do you know, I don't want to, because we don't have time for the second part. If I want to do this volume, what should I do? Integration by parts. So you do the integration by parts and put it here and then subtract, you get the volume of the vase. Okay, but if I wanted to start from the one above, then I have to construct everything myself. Yes? So then it means that it's very good, by the way, when you go home, because we don't have time for it. You go home and try to find a formula for if you follow these rectangles to rotate. Okay? But one more thing that I want to mention here, I want to find this vase volume by solid of revolution. So let me draw another picture for you. Then you see that you have to recognize which method is useful. So for example, if I have this scenario, and then instead of having vertical rectangles, let me choose horizontal rectangles. So in this case, it is the cylindrical shell method, but in this case, it is the solid of revolution method. Yes? So it means that for this case, I have to find the formula for the volume of revolution. What was it? It was pi integral y squared dx. The lowest value of x goes from a to the highest value b. But do you remember, this was the formula of solid of revolution if I am rotating about the x-axis. Yes? But I am rotating about the y-axis. So the formula will be pi integral y goes to from c to d, for example, x squared dy. Yes? Okay, but let me write the integral for you here. Can you help me to write the integral for this case? Do you understand what I am doing? In the solid of revolution, the normal one, I was rotating about the x-axis and I got this formula. Now I am rotating, this is the solid of revolution. I am rotating about the y-axis. I will get the same formula, the only difference is that the role of x and y will be changed. So this is the formula. I am changing the roles of x and y. But can you help me to write it in my problem now? So in my problem I have to write pi. The lowest value of y is what? 0. The highest value of y is what? Is 1. So, and then dy is just dy. But I have to write x as a function of y this time. So what is that? Arc sine. Yes, because my original function is this one. Is this function invertible? Yes, on this region it is invertible because it is strictly increasing. So this means from here I have to write x equals to arc sine of what? Y. This is x and put it there. So this becomes arc sine y to power 2. I really want you to go home and do these problems because if you can manage this problem on every aspect, this rectangle, and these kinds of rectangles, you should be able to get the final answer. And this is also an integration by parts, but a harder one. So it's also good to go home and do this one. For this one, do this trick. Take arc sine of y to be a new variable. First do the substitution and then integration by parts. Okay? You will immediately see that you will get the same integral back somehow. Okay? So, I want you to understand, this was a good question, even though the calculations are not very heavy. The first thing is that if you consider and calculate this volume, this is not the volume of the ace, so you have to understand that the volume of the ace is the green one rotated. Okay? And then there are 3 methods to solve this one. Considering these rectangles, which we didn't do that. Considering these rectangles, but I have to subtract it from the total volume. Or completely change my strategy, go from cylindrical shells to solid of revolutions. Then I have to face and solve a harder integral. This is also, I think, in your book. This is integration by parts, but usually everyone knows that this is an integration by part. Might be it is harder for you to do this by part, but that's also doable. Yes.
Can we do it by expressing dy instead of x? I mean in the last integral.
Yeah. No. Because now I am taking these rectangles. So in these rectangles, y is changing. So I have to write dy. It means my variable is y, not x. I have to write x in terms of y. I cannot write x squared dy and say that x is constant, I pull it out. If you mean something like that.
No, I meant like writing that dy is cos x dx and then doing that way.
Okay, but then what do you want to put for? Yes, that is correct, but you have to do it, but this will also change. Dy becomes cos x dx, but arc sine will also be
X squared?
X squared. So in the end, it becomes x squared cosine x dx.
Yeah.
That's correct. Then it has to do it 2 times. That's an integration by parts, but because x appears with power 2, you have to do integration by parts 2 times. But here you just need to do integration by parts 1 time.
Alright.
Yes? So that's what I'm saying. Yes, you are completely correct in that case. But then you have to do it 2 times. So in principle, this integration by parts is harder than calculating this integration by parts. Yes?
For the method where we consider the rectangles on the top, right?
Yes.
In the cylindrical shells formula, the reason we have the f of x in there is because we are multiplying by the height of the shell.
But the height will be 1 minus f of x this time.
Exactly.
Yes.
So we just replace, instead of writing sin x, we just Right, 1 minus sine.
Yes, exactly.
Yes,
Either
one.
you do it in that way, or this is the total volume minus that volume. Yeah, that's exactly correct. But I want you to play around with these concepts once at least, so that you learn it. Otherwise you will start forgetting about it. Okay, so let us go to the next part of the lesson. So here we want to talk first about the arc length. Okay, so what do I mean by arc length? So if you have an arc on the plane, for example, one part of the graph of a function is usually an arc. Even if it is a straight line, we still can call it an arc. But the point is that if I give you this function, for example, this function has a graph. Let us focus on one part of the graph from A to B. And then I want to find the length of this arc. What do I mean by the length of the arc? For example, you can imagine a piece of thread. You put one part of the thread, the starting point of the thread here, and you bend your thread so that it overlaps with your graph exactly. And then when you reach here, you cut that, and then you will have a piece of thread. You make it stretched and taut, and then you measure it with the ruler. That number is called this arc length, the length of the arc. So if you imagine an ant moving on this arc, the distance that ant travels is called the arc length. We want to find a formula for this arc length. Okay? What we consider here is that this function f is continuous. Moreover, f prime is also continuous. Okay, and then we want to find this arc length. So let me show it with L. Arc length. I want to find a formula for L. Okay, so intuitively we can imagine that I chop this curve into very small parts and then approximate this with a polygon line. For example, let me choose this point and the next point and the next point, etc. and then start connecting them. Yes? Calculating this length of this blue one is very simple because each piece is a straight line. And in principle, if I know the coordinates, I can find the length of this arc, the next one, the next one, the next one, and start adding them all. Of course, what you get is an approximation to what I want. There is no guarantee, as you see, there are little bit deviation between these blue lines and these real curves. Exactly as if you have a circle. If I want to exaggerate a little bit, if I connect this point to this point, this length is not the arc length, it is shorter than the arc length. Okay, but if I start chopping it to more and more pieces and add them up, the sum becomes closer to the arc length. Okay, so for example, let us concentrate on one of them. So let me take one of them and draw it a little bit exaggerated here for you. Okay, for example, like this. Yes, and then this is your blue line. So if I call this one ds, and then this one dx, and of course this one dy, and then I use Pythagoras theorem, I can write ds squared is equal to dx squared. I know what will happen now, but let us just write it down. So dx squared plus dy squared. And then if I ask you what is dy, dy is the derivative of my function multiplied by dx. So I can put it here. So this becomes dx squared plus f prime x dx to power 2. And then it becomes 1 plus f prime of x to power 2. And then I have dx to power 2. Okay? And then if I take the square root, so ds becomes the square root of that expression. And then I have dx. So you see what happens at the end of the day, I will have my infinitesimal, not second order. Okay, so this is this small part, okay, which I want to approximate it with the arc length if dx is very small, and then of course dy is also very small. So this means the arc length that I am looking for is just the integral of this. And then I go from A to B. So this will be from A to B. This is a hand wavy of doing it. There is a more precise way of doing it. If we have time, I will come back to it. But let me first finish what we are supposed to do. And this is the formula you have to remember for the arc length. So for example, do you think I can use this formula to find the circumference of a sphere, of a circle? Yes, because the reason that we cannot do it because you don't learn the integration techniques for doing it. Okay? Yes, we can do it, by the way, I think. So let us do it once. This is not one of my examples, but let us test. If I want to do that, let me draw a semicircle here with radius r. I want to find the circumference of a circle. If I calculate this arc length and multiply it by 2, I am done. But in order to do that, what I need my function. So hopefully you know what is your function. Is the square root of r squared minus x squared. So what I need in my formula is derivative. So f prime of x becomes minus x divided by square root of r squared minus x squared. I simplify 2's. But I need more. I need 1 plus f prime of x to power 2. So it becomes 1 plus x squared divided by r squared minus x squared. I take the common denominator, so it becomes r squared divided by r squared minus x squared. But then I take a square root. So this means finally 1 plus f prime of x to power 2 is r divided by square root of r squared minus x squared. Yes? Okay, so let us put it in the formula. So L in this very simple case becomes what? Integral from minus r to r. The least value for x is minus r, the highest value is r. So it goes from minus r to r. And then I put this expression, which is in the formula. I calculated this and put it there. Do you know how to calculate this now? Do you remember this? Any formula related to this?
Sorry.
It's arc sine.
Yeah.
Yes. So first of all, it is even. So I multiply it by 2. I pull r out, and I go from 0 to r dx divided by square root of r squared minus x. But if you refresh your memory, this is arc sine. So this is 2r arc sine of x over r. But I have to run it from 0 to r. Yes? If I put r, it becomes arc sine of 1, which is pi over 2. This is r. I was worried about where the r is. So 2r, and if I put r, it becomes pi over 2. And if I put 0, arc sine of 0 is 0. So it becomes pi r. So this is the length of that curve, which is half of the circumference. So this means that the circumference of the circle is 2 times this quantity, which is the famous 2 pi r. Yes, that's correct. But usually these simple questions are not given in the exam, so let us do them. Sometimes they are hard, so you have to be good in integration. Both of them I have taken it from your book, so let us do it. Okay. So let me do the first one. By the way, you might think that they are very simple because the functions involved are extremely simple. For example, in the first case, it is x to power 2/3. So y equals to x to power 2/3 and the bounds are given to be 1 and 8. Yes? Okay, so I want to solve this one, even though this function is extremely simple function, but this is not always easy to calculate the arc length. For example, I don't know if you know, if you want to do the same calculation for an ellipse, the integral is one of those integrals that cannot be done analytically in terms of famous functions. And this will open up a new branch of mathematics called elliptic functions. Okay, so be careful. Finding these integrals are not that easy sometimes. So the person who wants to design these questions, they have to be very careful about designing such a way that you really can do it. Okay, so we want to solve this one. We want to find the length of this curve if x goes from 1 to 8. Okay, so what I need my formulas, so I should have it in my mind. And then this is my function y prime. This is my function y. I need y prime. So it's very simple. It becomes 2 over 3 x to power minus a third. But I need this combination. I need 1 plus y prime to power 2. Square root of 1 plus f prime to power 2. I have to calculate this one. This one you have to be very careful, because if you can manage to do this correctly, if it is possible, then more or less you are done. So let us do that. It becomes a square root of 1 plus this one to power 2, which becomes 4 over... Oh, might be this is one of those integrals you cannot calculate. I was careless. Okay, let me continue. Yes. If we cannot calculate it, we leave it at the end and go to the next one, because the next one I did it is possible at this level. Okay, so if you do this one up to here, I get this one. Do you agree with my calculations? And then I will try to simplify this a little bit. How, for example? I will get rid of negative exponents. So 1 plus 4 over 9 x to power 2 over 3. Yeah, I think we will be in trouble finally. Let me see. Okay, so let me take the common denominator. So if I take the common denominator, it becomes 2/3 plus 4. And then I have 9 x to power 2/3. Do you agree with me? It seems correct. But then the square root of the denominator can be written as 3x to power 1/3. In principle, I have to put absolute value, but I don't need absolute value because x is between 1 and 8. And then I have this one. I think okay, let us see how it goes. So in exam, do it in 2 steps. It needs absolute value because I am taking second root, but absolute value is dropped because I am working between 1 and 8. Okay, but then I have to integrate this. Okay, even for this simple function, the integral is a little bit hard, but let us see if we can do it. So L becomes integral of this expression from 1 to 8. Do you think we can do it, or we need more techniques? Any ideas? U substitution should work. But let me take this one to be U. This one, if you remember, I told you something about this trick as well. So let me take this one to be U, but don't differentiate immediately. Raise it to power 2 first, and then differentiate. If I differentiate, the left-hand side becomes 2u du. The right hand side 2/3 go down, so it becomes 6x to power minus 1 over 3 dx. Is that right? Yeah, that's correct. And then I bring this down and I simplify 2 3 dx over x to power. Okay, that's working. Because I needed this combination. This combination is a third of this expression. Yes. Let me wait a little bit. Is that understandable? Okay, so everything, but now I have to also change the limits. So when x goes from 1 to 8, what happens to u? Instead of x I put 1, it becomes a square root of 13. Instead of x I put 8, 8 to power 2/3 is 4, 40. Yes. So this means that n is integral. Instead of 1 to 8, I go from square root of 13 to square root of 40. Instead of this expression, I put u. And then, I just put u. Instead of dx over x to power 1/3, I put 1 over 3 u du. Yes? And there was also 1/3 here, so I pull it out. So 1/3 by 1/3 is 1 over 9. Integral from square root of 13, square root of 40, and then I have u squared du. Yes? And this is elementary now. So this becomes a third, so it is 1 over 27. U to power 3 from square root of 13 to a square root of 40. So this is nothing except 1 over 27, 40 square root of 40, minus 13 square root of 13. The length unit, a weird number, but that is what it is. But it was doable. I was thinking that we need trigonometric substitutions in the middle of the way.